All right, welcome back. I hope you're having an amazing time so far. Our next speaker is Natesh Babu Arunachalam. He is a senior data scientist at Finicity. Please join me in welcoming him to our virtual stage.
Hi, everybody. Good afternoon. Hope you're having a great day so far. So as Patrick introduced, I'm Natesh. I'm currently at Finicity. Prior to this, I spent almost 3 years validating machine learning models at JPMorgan Chase. So today's discussion is going to revolve around drawing from my experience on how to best manage model risks that emerge from machine learning models. Motivating today's discussion, let's start off with our interactions with AI. I'm sure we all agree that AI is eating the world. AI is omnipotent almost today. In this slide, I just listed below a few of my interactions with AI in different forms and factors on a daily basis. And these are only the ones that came top of my mind. There could be many, many more. For example, Alexa Echo, voice recognition. It uses voice recognition techniques for a lot of fun things, and also, reminders, alarms, and so on. Apple Face ID uses face recognition techniques. Facebook Newsfeed uses ranking algorithm to optimize your feed, and of course, make money through ads for them. And Netflix, recommendation system, Reddit, personalization of your feed, Gmail's autocorrect. Banks use AI and ML in a variety of applications. It could range from fraud detection. It could range from you're scanning your checks when you do a remote deposit. It could be underwriting your auto loan, your credit cards, your mortgages, and so on. And lastly, Amazon's people also bought. Amazon uses a recommendation system to show you products that are similar to the ones that you are buying currently, and which other people have bought. And lastly, just highlighting one of a very interesting application of AI today is in the self-driving car domain. And from December 2019 to November 2020, self-driving cars almost drove 1.5 million miles with just slightly short of 5% failure rate, or what they call miles of disengagement, wherein the driver had to take control, which is a very impressive feat. Now, we have looked at the rewards or the benefits of AI, but AI is not a silver bullet. AI comes with its own sets of risks and biases. A few of the notable AI failures are here we have Steve Wozniak's tweet, which raised a storm with the Apple Card. So what happened in his case was he and his wife applied for the card, and they had joint accounts and joint assets. So technically, they should have got the same credit limit. But what ended up happening was Steve got a 10x credit limit compared to his wife. So this potentially indicates a gender bias in the model. The next example that we have here is researchers finding racial bias in hospital algorithm. What they found was healthier white patients were ranked the same as sicker black patients, which effectively meant some people were not getting the treatment that they needed. And the third example we have here is from the language domain. So this is a translation model between English and Hungarian. And the text that we put in English here is he's a nurse, she's a doctor, which gets translated into Hungarian. But when we do the reverse translation between Hungarian and English, the occupations for the genders get reversed. So this could, again, lead to a bias in the training data. This is probably what the model saw when it was being trained. But this, again, indicates a bias in the model that is not desirable. And here we see a face detection model on the right side, benchmarked for different companies. And what we notice here, a pattern that we notice, is the model performed poorer on darker skinned individuals compared to their lighter skinned counterparts. Again, this clearly points to a bias in the model. So here we are going to compare AI model versus statistical models. So not to say that modeling is new or anything like that. And statistical modeling, in fact, has been around for almost half a century now. And AI models also, in theory, have been around for almost that long. But the adoption of AI models in industries is a relatively new phenomenon. So let's look at why is AI ML models, or how are AI ML models different from their statistical counterparts? I've chosen to list this among 5 key dimensions. The first one is data set. Statistical models typically tend to use small unstructured data, whereas their MLA counterparts use large and unstructured data. And unstructured could mean text, images, and so on. And large could mean billions or even trillions of data points in some cases. The second dimension is modeling assumptions. When you're building a statistical model such as a linear regression or a logistic regression, you have a lot of assumptions accompanying it. For example, homoscedasticity, you have your linearity assumption and so on. Whereas for their MLM AI counterpart, there are relatively fewer assumptions. And a lot of times what ends up happening is people tend to throw the kitchen sink on the model and they expect good outputs, which may not necessarily be the case. The next dimension is that of feature engineering. For statistical models, feature engineering is extensive. There's a lot of handcrafting going on to create rich features. Whereas for MLAI models, it's a benefit in the sense that feature engineering is minimal because the model can extract the useful signal from the data itself, which is a huge benefit. The next dimension is that of model complexity. Typically, the statistical models tend to be less complex than their MLAI counterparts. And complexity is closely tied to the next dimension and the last dimension, which is model interpretability. Because statistical models are less complex, they tend to be more interpretable. For example, the coefficients in terms of a linear model, whereas MLA models are less interpretable and are more black boxy. Although there are techniques that are emerging today which help us interpret complex models, but they're still a work in progress. Now, let's look at model risk management of AI and ML models. So let's talk about SR 11.7. What this means, what this stands for, is a supervisory guidance issued by the Federal Reserve and the Office of the Comptroller of the Currency on April 4th, 2011. This is just 10 years old now. So 10 years ago, the regulatory bodies issued a guidance which basically laid out the model risk management framework that they expect banks to follow and the different stakeholders of the model risk management process and how effectively to manage model risks. So the first thing that they did was to define what a model meant. In their definition, model referred to a quantitative method, system, or approach that applies statistical, economic theories, techniques, and assumptions to transform input data into quantitative estimates. And why this definition is important to us is because this definition basically puts the ML and AI models that are used today under the remit of this particular guidance, because they effectively match what they mean by a model code. Secondly, it clearly lays out that model risk needs to be managed because it can have further ramifications in other dimensions. It could lead to financial loss for the company. It could lead to poor business and strategic decision making. And lastly, it could also lead to a bank's reputational damage. There's a headline risk component involved with a model, which is involved with model risk. And it also clearly lays out what is expected from the model validation teams. So SR 11.7 goes on to say that the validation should involve a degree of independence and from the model development and use. And that is because it needs to be free of judgment and bias. And there are 3 steps, 3 layers of defense in a bank's model risk management framework. The first layer of defense is the model development team, which actually develops the model. And the model validation team, which I was a part of at JP Morgan Chase, sits in the second layer of defense. And the internal audit is the third layer of defense. So model validation is tasked with evaluating the model once it's developed by the development team. So model validation team does it by looking at a few different dimensions. The first one is evaluating the conceptual soundness of the model. Is the model fit for purpose, etc.? The next dimension is outcome analysis. Is the model performance robust? Does it withhold a test of time? Or is it biased in any manner? And the last key thing that model validation teams do is pose effective challenge to the development team. And what I mean by this is to say, hey, you guys, the development team has used this model, but maybe this model is better for this particular task, or maybe we can tweak the model, or probably we can reduce the complexity of the model and so on. That's where the knowledge of the model validation team comes in. And the third layer, the internal audit, basically is an oversight function, which basically ensures that the policies, procedures, and standards are adhered to, and there is a robust framework in place to manage model risk. So now let's look at the actual ML model building pipeline. So in my view, there are 3 main stages in building ML models. The first stage is the pre-modeling phase. The next step is the modeling phase. And the third step is the model usage. The pre-modeling starts before you actually throw the data into the model. And it involves a few key steps, such as business rationale, understanding the model from a business perspective, selecting the data, making sure it's of the right quality, doing some initial variable selection / reduction. And the modeling step involves choosing the algorithm, the key metric, and the candidate model, analyzing its performance, benchmarking it. And lastly, the model usage deals with model interpretability, basically peeking under the hood. We will be talking about all these different dimensions in the next few slides. And one overarching theme that I want to point out is the regulatory compliance, which spans across all the three steps in choosing the right data, choosing the right model, and choosing the right sort of interpretability techniques, which are mandated by the regulations. So now let's look at the first component, which is business rationale. So this step deals with asking a lot of questions with regards to for example, does the model target variable align with the final business usage? And why this is important is because a lot of times models fail because they are not used as intended as how they were built. The next next very important question is what will the model be used for? Is it going to be used for rank ordering or forecasting? Because a rank ordering model could be something like a fraud detection or a marketing campaign response model, whereas a forecasting model could be a stock price prediction model. And both these two different kinds of models are different, and they come with their own corresponding metrics that need to be used. And the other important question that needs to be asked at this stage is how will the model be run? Is it going to be run in a real-time mode or in a batch process? And the reason this is important is imagine you're building a credit card real-time approval model, which basically means when you go swipe your card at a merchant, it gets approved or denied. That time you can't have a model that is so complex that it takes 5 minutes to give a result. It needs to be in like a few milliseconds time, the inference. So that's why this question is important. And the next question is, does the model comply with any regulatory requirements? For example, especially for consumer models, there are two very standard regulations. One is the ECOA, or the Equal Credit Opportunity Act, and one is the FCRA, Fair Credit Reporting Act. So a model would need to comply with both these regulations before it actually goes into production. And the last question would be, how often will the model be retrained? Because this would again contribute to how the risks are managed. Is it going to be on an everyday basis, quarterly basis, or sometimes build and forget? And this step, one crucial component of this step in the model building phase is that multiple teams come together to align with why the model is being built. We need teams from legal, compliance, the model development team, the model validation team, the business users, and finally, but most importantly, the IT/infrastructure team. So it's a synchronized process which would only succeed if all these teams are in alignment. And the next step is data. So in this step, there could be risks that come from multiple dimensions, and we would be going through each dimension. The first dimension is that of data source. And the questions that we need to ask for this particular risk dimension is the data internal or external? Depending on the answer to this question, the mitigation strategy would be different. For example, if it's internal, there's high likelihood that it comes from a data warehouse that is being monitored closely and periodically, and it's more kosher in a sense. But if it's coming from external sources, then we need to make sure that the data quality is right and so on. The next key question is, will the data continue to be available in the future? And why this is important is because let's say that we had 3 sources of data, like 2 internal and then 1 vendor source, but the vendor source stops flowing into the company 3 months down the line. Then this model would basically suffer because a huge data source is not going to be available in the future. The next dimension is that of data quality, which we touched upon briefly before. We need to ensure that the data quality is of the highest level. And also the quality needs to be monitored continuously, and the validation team needs to make sure that there's a plan in place for ensuring data quality. The next risk dimension is that of data selection. So this is again a very important step, because if this step is not done right, we could end up with a biased model. The first question for this dimension is, what is the scope of this model? What data is in the scope? Are there any exclusions? And if there are, are they clearly specified? Because the exclusions of the modeling data would effectively drive the limitations of the model and how it can be used. For example, if there's a model that's built on North America data, then that model cannot be extended directly to rest of the world. We need to make sure that there are checks and balances before we actually roll out the model to the entire world. Secondly, what about seasonality? Seasonality can be very important for models because there could be spikes in the data, which we would miss if we don't account for the seasonality. For example, holiday season is a very important factor from a seasonality perspective for spending models. The next key question, what about sampling bias? Have we sampled correctly? And is there any upsampling, downsampling? And if there are any, is it a random downsampling or is it a stratified downsampling? So there are a lot of questions at this step which we need to ask to make sure that the sampling is done right and the modeling sample is reflective of the true distribution. The next step is to split the data between the train, validation, and test. These are the three data sets that are commonly used to build a model. And at this step, it's very important to make sure that there's no data leakage, because if there is data leakage, you would get a biased model performance, and you might interpret the model performance as something good, but in reality, it could turn out to be quite poor. Continuing the data theme, the first risk dimension after you have the train, test, validation data is to actually prepare the data for the model. So at this step, you start off with a few model-dependent transformations if they are applicable. Like for example, if it's a word model, like an NLP model, you might want to start off with stemming, lemmatizing, or stop word removal if applicable. Or if it's a regression model, you might want to do some sort of standardizing or normalizing. And the next thing is, what about missing data treatment? And missing data treatment commonly is done by a mean imputation or a median imputation, but that need not be the right methodology all the time, because the missing data treatment should depend on the missingness mechanism. And what I mean by that is there are multiple missingness mechanisms, for example, missing at random, not missing at random, and so on. And each of them would require corresponding treatment. The next key thing is outlier treatment. For example, will the model be built on COVID period data, or is that particular period removed from the modeling sample? This is important because this period can technically be an outlier in your data, and we need to treat it accordingly. And the last step in the data preparation phase is to make sure that the variables are stable. And this step is important because if we build a model on variables that are not stable, then we would have a model that drifts in the production and the performance would deteriorate very quickly, which is not desirable. And the ways to identify variable stability, one of the methods could be using population stability index and comparing the metric between the training and validation and so on. The next key dimension in the data theme is that of variable selection. So the first one is, are all the variables that are being considered apt for the business application? So we need to have a qualitative run through of the variables to make sure that we're not using variables that add more noise than signal to the model. The next question that we need to ask here is it possible to detect multicollinearity at this stage? And if yes, we can remove variables and make the dimension much smaller and more manageable for the model. The next key question is, if there are categorical variables, most models require them to be encoded because the models would only take in ones or zeros and not text values, and they need to be encoded. And this will also help to reduce the dimensionality depending on the technique that we use. And even categorical variable encoding has multiple ways of doing, and we need to make sure that we choose the right methodology. And last but not the least, we definitely need to make sure that the variables that are being considered or used in the model are compliant with the applicable regulations/contracts. What I mean by this is, for example, if you're building an auto insurance model, there are a lot of states that prohibit certain variables to be used, such as race, religion, gender, and so on. So we need to make sure that the model is compliant with all the existing regulations. So now we have seen the business rationale. So let's say we are all aligned and we know why the model is being built. And we also have the right data. We have the right modeling data. We have the validation data, etc. So now it's actually the time to fit the model. At this stage, we start off with the first dimension, which is the model itself. So what algorithm are we choosing? Is it reasonable for this application? What is the key metric of the model? Is it again aligned with the business usage? Um, what kind of hyperparameter tuning are we doing? There are again multiple ways of doing it, and we need to justify which method we're choosing and why. And which would inform the next question, which is the model over or under parameterized? An over parameterized model is not decided because it would not generalize well usually. And lastly, is there any transformation required for the model output? For example, if it's a probability model, it's going to give values between 0 and 1. But say we need a FICO score type output, then it's going to scale it back. And we need to make sure we analyze the model outcome to make sure that it's robust and it's generalizing well in production. And lastly, we need to also keep in mind that vendor models require their own policies and standards, and we need to ensure that sufficient details are provided. Lastly, we have the model interpretability slash bias. And this is the realm of model usage. And this is when the model is actually built. So in model interpretability, we have a few techniques. The first one is global explainability. Here we are actually peeking under the hood of the model to make sure that the top variables make business sense. This is crucial because it helps us understand what the model is fitting on and what it's not. And the next one is local explainability. For some use cases, we need observation level explanations for the downstream model user. And there are a few methodologies to handle this. For example, SHAP and LINE. These are two popular techniques. And the next one is, what about disparate impact? Like of some of the examples we talked about previously, are we discriminating against protected classes, which is a complete no-no. And this goes into the fairness and bias evaluation of the model. And lastly, again, touching back on the regulatory requirements, we need to make sure they are met. Next, we'll need to look at the model deployment and monitoring to make sure that it's deployed fine. The first question we need to ask here is, okay, we develop the model in an environment, but is it reflecting in the production environment? And we need to do some implementation testing and make sure that the results are satisfactory. And only then we need to roll it out in the production environment. The next question is, what is the frequency of monitoring? We need to make sure that we monitor the model because we can't just put it in the production and forget about it. We need to periodically monitor it to make sure that the model is not deteriorating and so on. And what metrics would be monitored? So usually we need to monitor a key metric, which could be a ranking metric or a forecasting metric, along with a guardrail metric, which could be something that supplements or complements the key metric. And the next one is, we need metrics to identify data drift because they can be a leading indicator of potential model failure. And we need to make sure that we have triggers for recalibration preset before we actually roll out the model in production. For example, if the AUC of the model drops below 15%, then we are going to recalibrate the model. And these triggers need to be well defined. And again, frequency of retraining, we need to have a schedule in place so that we make sure that the model is robust in production. And the last interesting topic that is really applicable for AI ML models is that of model attacks. Firstly, adversarial inputs. What I mean by this is malicious actors could poison the model by feeding it bad examples. And a very interesting example of this is for a self-driving car. People actually place stickers on the road in front of it, and the car actually changed the lanes because it saw the stickers. So this is something that needs to be identified and mitigated. And this closely ties in with the next point, which is that of training data poisoning, which is exhibited, actually was exhibited by one of Microsoft's chatbot robots called Tay, which Microsoft rolled out as a Twitter bot and pulled it down in just 16 hours, because within 16 hours, people, internet trolls fed it a lot of malicious data and the bot turned rogue. So they had to pull it down within 16 hours. So some key principles to keep in mind while building ML models, just to summarize, are garbage in, garbage out. Selection bias. We need to make sure that the sample is reflective of the distribution. The bias variance trade-off. We need to make sure that the model is not overfit. And lastly, Occam's razor. We need to make everything simple as long as we are not losing performance. To summarize, model risk management is not new, but AI models are. And why AI models pose their own unique set of risks is because they are evolving rapidly. We have models coming in every month and weeks. Interpretability of AI models can be complex. They pose unique security and privacy concerns. And lastly, a lot of companies tend to depend on external models, which come with their own unique set of risks, which need to be identified and mitigated appropriately. Thanks for attending.
Wow, thank you so much. That was amazing. And I know this virtual audience loved hearing your insights today and is giving you a huge virtual round of applause. If you could stop sharing your slides, please, we'll send the audience to their next session. Thanks so much again. For the audience, it's time for you to make your way to your next session. Along the way, make sure you accept your connection request and take some time to check out our amazing exhibits. Thanks so much, and we'll see you around.